look at something called the fundamental counting principle. And this is the beginnings of getting into things like probability and statistics. But before we can get into all that kind of stuff, we've got to look at how we count things. So, I'm going to start off by looking at a very basic example and saying we have 3 letters, and maybe visualize them as being on 3 cards. So we have 3 cards, A, B, and C. And what I want to do is arrange these and figure out how many different ways I can arrange these 3 letters or cards. Obviously what we have is one sitting here, and then I could do something like maybe I could put B, A, C, and so on and so forth. Now, rather than to try to brainstorm it and list it manually and kind of hope that I don't miss any, I'm going to use an interesting technique that has some good and some bad stuff to it. It's called a tree diagram. So let me just show you what that's going to look like. Now, I'm going to need the room for this. So when we lay down the first card, we put down the first card, it could be either an A, a B, or a C. So you see what I've done is I've listed each possibility for the first letter. And then suppose we put down an A. What choices do we have for the second? Well, it could either be a B or a C. And if we put a B first, then we either have an A or a C. And if we put the C, we either have an A or a B. So what you can see I'm doing here is I'm creating branches of possible outcomes, branches of possibilities. If we put down an A followed by a B, we have no choice. The last card that we put down would be the C card. A followed by C, last choice is B. B followed by A, last choice C. B, C followed by A. C, A followed by B. And C, B followed by A. Now this covers every possibility that there is. And what you can say is, well, how many total branches are there? If I follow each branch branch representing a possible combination. So what we have here is a total of 6. 6 different possible ways of arranging 3 letters or 3 cards. Now that's called a tree diagram. It can be very useful, but I think you can probably guess what the weaknesses of a tree diagram might be. Let me change the parameters of this example, and I think you'll get the idea. Suppose I was going to lay down a deck of playing cards. Instead of a choice of A, B, or C, I have 52 different choices for the first card. That's pretty hard to draw. And then I tried to draw more branches. Well, I put down like whatever, a jack of clubs. Well, now I got 51 more cards. I mean, you can't draw it. Okay, so a tree diagram is really good as a way of visualizing, but sometimes you have a lot of limitations because you can't draw it. It's just too much information trying to be compressed into one drawing. So we use another possibility. And I have just enough room under my tree diagram to show you this one. We simply look at the outcomes. And it really is based on sort of counting branches. It's kind of like saying, how many of these first limbs do I have? Well, it's like saying I have 3 of them first branches. And then each one of these splits into 2. So it's kind of like saying 3 times for each and every one of these 3 times 2. Because each one has 2 sort of split branches. And then the last one is just a single branch, so it's like saying times 1. And you'll see what we get is 3 times 2 times 1. Well, my goodness, oh, that's 6. Oh. So you can kind of work it out by counting the number of times that a branch would split at each step of the way. Another way of thinking about this is not really to think of a tree diagram at all. Let me just write it again to kind of show you that method. I would just look at it like this and say, well, I'm going to lay down 3 cards. How many choices do I have for that first card? Well, I have 3. How many choices now? Once I've laid a card down, how many choices do I have? Well, I only have 2. And lastly, I've laid down the 2 cards already. So on the third go of it here, there's only 1 choice. It's a slightly different way of thinking about it than the sort of based on the tree diagram approach. Okay, let's do an example or two of the fundamental counting principle and see how it might help us pick out some real life situations. So, I think in the first example, we're going to go for breakfast. Okay, so in this example, we get into the restaurant and we look at their special. They got a big sort of a sign at the front, and they say they got a breakfast special. And they say, well, the first thing you could get in the special are eggs, and you can get them scrambled, you can get them poached, you can get them, what else, hard-boiled, what else can you, over easy. And I know there's many other ways to do eggs, but that's all they give you here. So that's the egg business. Then they say, what else we got here? Okay, you get ham, bacon, or sausage. Okay, so there we go. A couple of things here, a couple of choices here. Then we're going to say you get, how about toast? Or an English muffin. And lastly, they say you get your choice of coffee or tea or some kind of juice. Okay, so now what we're thinking here, because we're mathematicians, we're sitting in that restaurant, and we're thinking, just hold your horses, everybody. If everybody in the group was to have a different breakfast, okay, so no combination being the same. Okay, so one person might have scrambled, ham, toast, and coffee. Somebody else might have poached, ham, toast, and coffee. We would consider those to be different. How many different ways are there to put together breakfasts in this particular cafe? So we're looking at counting up all the different ways of combining these foods. So here's all there is to it. How many choices do you have here? You have 4 choices. Okay? If you think of the tree diagram, that's like saying you have 4 main branches. You go to the next level, and each branch splits 3 ways. You can have ham, bacon, or sausage. So that's times 3 choices there. And then times toast or English muffin, that's 2. And lastly, coffee, tea, or juice, 3. All you got to do is multiply these things together, and you get 72 possible different breakfast combinations. So that's actually quite a bit when you think about it. All right. Let's do a couple more examples that look at something like a padlock. Okay, and for this one, the numbers are probably going to get pretty big. Might be reaching for a calculator. But let's see. Okay, let's say you have a padlock. And you've got numbers on the padlock ranging from 0 to 59. Okay, so that's a padlock that we have here, and we require 3 numbers in the combination. So 3 numbers in the combination, in the combo. Okay, how many possible combinations are there? How many different combinations are there? pretty fair question, especially if you're in the padlock making business. You'd kind of like to be able to tell your customers, well, you know, we've got 40 billion different combinations. If it's mathematically backed, you have a pretty good sales pitch. So let's have a look. Okay, I'm going to use just sort of a counting technique here. We have 3 numerical levels here, 3 levels of choices. In the first one, we can choose any number from 0 to 59. Now that would be 60 numbers all together, because we're including the 0 as well as the 59. And at the next level, so we would go to the first number, then we can go to a second choice, also ranging from 0 to 59. And lastly, we still have 60 choices. So let's reach for the calculator and see what 60 times 60 times 60 is, or 60 cubed. Well, that's not too bad. 216,000. That's quite a few. What are the odds there that someone's going to be able to guess your combination? That's not too bad. Okay. Now I'm going to look at the same situation with one twist. Okay. So now we're going to say no repeating numbers. In the combination. So now, how many choices do we have? This is just a little extra twist here. If we didn't allow any repetition, we'd still have 60 numbers for our first choice. But remember, one of those numbers has now been used. So you only get 59 choices for your second number. So you can't use the first one again. And lastly, you only get 58. The reason is because you can't use the first or the second number again. There's no repetition allowed. So let's have a look. What's 69 or 60 times 59 times 58? Well, we lose a little bit. 205,000 and 320. So we lose a little bit of the numbers, but not a whole lot. And still pretty good padlock. Anyway, that's the fundamental counting principle. So we'll catch you later.